Okay, so there are 8 questions, 8 free response, just like we had before on all of our other various exams. So 8 free response, and then there are 40 multiple choice. Now the way that I do the free response is I pick one question from each exam. So like for example, this one just had 3 questions, so I might pick a question like this, but then I would only give it 2 sections. So like I might get rid of this section and this section, and then maybe just like this and this, for example. I know that especially for this one where I'm taking 5 parts and condensing them down to 2. But like I said, you're probably going to see one like this where you have to do the force vectors. So I give you 2 questions from each exam, and each of those will have 2 sub-questions. So that means that you'll have a total of 8 with 4 different questions, 1 from each exam, and each will have 2 parts. And then I go through the exam and I pick questions. So for example, if I were to pick this question, I would give you this question, but I would give you a different configuration of charges. If you go back and look at the other old exams, of course you see similar questions to this one, for example, or similar questions to this one, or similar questions to this one. I mean, all of the exams have variations on those problems because that's how I write the exams. I look back at my old exams and I think, okay, I have this topic I want to assess you on. What are some different ways that I could ask that question? So I say that to say that it's useful for you to work the old exams, but it's also useful for you to work the old exams. Like it's useful to work the exams from this semester, but after you've exhausted those, then you can go back and work previous semester's exams, and that'll help you too. Okay? Yeah, so that's it. 8 free response, 40 multiple choice. There are a total of 150 points. So just be aware that this does carry more weight than exams 1 through 4. But you've seen it all, and you've been tested on it already, so, I'm hoping that you should do better on that. So let's, on this exam than on the 4 previous exams. Let's just do this one. So I won't work through all the numbers, but I'll step you through the different steps that you have to do this one. So a student asked about this. I want to find the electric field at point A. The first thing that you need to do is to find the sketch in the 2 electric field vectors. Remember, you imagine that there was a positive charge there, and then ask yourself, what is the direction of the force that either of these charges would feel? So I'd have an electric field then in that direction, I'll call that E1, and then I'd also have an electric field in that direction, I'll call that E2. Okay? Your next step would be to figure out what is the angle. What is this angle right here? Notice that I have a triangle where this is the angle theta, this is side 4, this is side 3. So that angle theta, which you can find with the inverse tan, it would be 37 degrees. And then you also need to find what is this distance right here. Of course, that's a 3, 4, 5 triangle, so that distance is 5 meters. Then you would calculate E1 and E2. I'll just do E1 right here. That's KQ over R squared. That's going to be 9 times 10 to the 9th. Q for Q1 is 32 times 10 to the minus 9. I try to make the numbers work out easily, so notice here the 10 to the 9th and 10 to the minus 9 come in. Hey, yeah. And then divide by the distance. That's going to be 32 divided by the distance, which is 4 squared. So that cancels with that. That gives me 2. So that gives me a total electric field of 18 newtons per coulomb. Remember, the units for electric field are either newtons per coulomb, that's a force per unit charge, or it can be in volts per meter as well. It's just a little aside. All right, so that's an 18 right there. Once you get the magnitudes of E1 and E2, your next step is to figure out what are the x and y components. So you do E2x. That's going to be E2 times cosine of theta. And then E2y will be E2 sine of theta. So you find those x and y components. Again, I'm not going to calculate them here, but you can look back on the video and see what they are, try them on your own. But once you find that, find the x and y components, I find that it's useful to redraw the vectors. So I'd have, for example, E1 right here. E1 is 18 newtons per coulomb. And then I'd have E2y right here and E2x right here. So that reminds me that I have to take the difference. So now when I find my two final vectors, this vector right here is going to be E1 minus E2x, because E2x was in the negative direction, and then this vector would be E2y. Then, whatever those values are, they're just numbers, right? So I take the difference in E1 and E2x. Then, if I want to find the magnitude, I do the square root of EX squared plus EY squared. And then I'd also find the angle, recognizing that my angle is this angle right here. So theta would be the inverse tan of, what is that, EY over EX. Opposite over adjacent. So that's how you would find the magnitude and the direction of that electric field. Okay? I know that that's a lot for that problem, but you're going to see it. So be ready for it. I will ask you to find the electric field, either the magnitude and or direction. I might also ask you the potential. Remember, the potential is quite a bit easier. So if I wanted to know the potential at this point right here, the potential is equal to KQ1 over R1 squared plus KQ2 over R2 squared. And then also remember that you have to keep the signs. So since Q2 is negative, I'd have 9 times 10 to the 9th, 32 times 10 to the minus 9, divided by the distance to that, which is 4 squared. Excuse me, not squared, I'm sorry. No square right here. KQ over R divided by 4. That's for potential. I'm sorry. This is not electric field. This is potential. So the potential plus 9 times 10 to the 9th times 25 times 10 to the minus 9, but it's negative, divided by 5. And then whatever that value is, that's your potential. Okay? That's quick, but you are going to see it on the exam. That'll be problem number 1. So make sure that you're ready for it. And it's probably one of the harder problems that you'll have, right? Because there's a lot of steps involved in the vectors, but it's really my last chance to make sure that you know how to add vectors, which is probably one of the most important mathematical things that you can do this semester. Okay? There's some other... I guess I just showed you what my question is from exam 1, right? Because I told you that. I'm not going to tell you any others, I'm sorry. But some of these other things come up in multiple choice questions too. So it's still useful to review these for your response. Okay, that was a question that a student had asked that wasn't able to come. But do y'all have specific questions that you want me to address from either the exams 1, 2, 3, or 4?
Exam 3, I struggled with the most.
Okay. That was this one, right? With the RC circuits?
Yes, I think the free response, like, I'm sure, like, to go over it if it's on the exam, but I didn't struggle with that. It was more so, like, how you know with the right-hand rule with, watch on the line, like number 14 and number 17.
Okay. There were a lot of right-hand rule problems on this exam, so you can imagine there'll be a significant number on your final, right? 14, and what was the other one? 17. Yeah, so these are similar problems. Let's look at both of them. Number 14 is probably a little bit easier than 17. I have 2 wires that generate a magnetic field, and I want to find the direction of the resulting magnetic field. Remember, we have 3 applications of the right-hand rule. This is that 3rd application, where I let my thumb go in the direction of my current, and then my fingers wrap around. So for example, if my current is out of the page, that means that the magnetic field is going to go in that direction. My thumb goes out of there, and my fingers wrap around in a counterclockwise direction. So due to this wire, I'm going to have a magnetic field in that direction. And then due to this wire, let's see, if I let my thumb go in the direction of the current, then that means I'm going to have a magnetic field in that direction. So I have these 2 magnetic fields that add up. That means that the net magnetic field is going to be down and in this direction. So that's why the answer to that one is D.
Wait,
Okay, let's see, did I do it wrong? Oh, that's right.
Are we pointing our thumb to the object, or are we pointing our thumb to the arrow?
You let your thumb go in the direction of the current. So right here, where it's coming out of the page, my thumb comes out of the page, and then my fingers wrap around, giving me the magnetic field. Let me draw it on here. So the magnetic field then would go around in a circle like this. So at this point, the magnetic field would be tangent to that circle. It would go around in a counterclockwise direction. It's helpful to draw the circle, but I don't usually do it because it gets too messy. But your magnetic field does go around in a circular path around that wire, okay? And then at whatever point I'm looking at, like if my point was over here, my magnetic field goes tangent to that circle. Let's look at this other one because it's really similar to this one, but it had a little twist at the end. So here I have 4 wires, and I want to know what is the force on wire at A, on this wire right here. So I imagine, if I have a wire that's into the page, the magnetic field goes around in a clockwise direction, like that. So if I imagine each of these, let's take the top one first. We'll do this one. If it goes around in a clockwise direction, that means here, the magnetic field is in that direction. Another good way to think about this is if I draw a line between these 2 wires, between these 2 points in space, the magnetic field is going to be perpendicular to that line. Okay, so if I look at this wire, it's going to be like that. And then if I look at this wire right here, it's going to have a magnetic field in that direction. Now those 3 vectors, I have one that points up, one that goes off to the side, and the other that goes to the side. Those 3 vectors are going to give me a net vector that will only be up in this direction. Because these 2 vectors that are off to the side, they're going to each have an x component that will cancel each other out. So the net vector will only be in the y direction. So if I get rid of all this, my magnetic field is in that direction. And so now this becomes a lot like just one of the simple problems that we've done. I have a current that is into the page and a magnetic field that is up, and I want to know what is the force. Remember, this was the second application of the right-hand rule, where I let my index finger go in the direction of the wire, my middle finger go in the direction of B, and then my thumb gives the direction of the force. So if I do that here, I get a force that is to the right. That's my force. So C would be the right answer. That's a hard question. There's several steps you have to take. But, if it was easy, everybody would be doing it, right? Yeah. Everybody be a doctor, everybody be a chemist, or everybody be a whatever, pharmacist. Or...
Did everyone do like 80% of last
Oh, I haven't checked. I'm sorry. I will... Did you just roll your eyes at me?
No.
Okay. I suspect they did. Actually, I think I told y'all were at 40%. Y'all were actually a little higher than that, maybe more like at 50 or 60%. So I think you probably did. Okay? Before I announced it to y'all. Y'all were not that far from it. Okay. What else? You have other... Does that help with that question?
Yeah.
Those are good.
Perpendicular helped a lot.
Yeah, I find that helpful for me too.
Yeah.
Drawing the circle helps, but then it just gets messy.
Yeah.
But if you draw a perpendicular line... Yeah. Okay. What else? Yeah, number 19. Yeah, so this is like a mass spectrometer. When you have a particle in a magnetic field, a charged particle, it will travel in a circular path. Just pick a point. It doesn't really matter what point you pick. Like, for example, if I pick a point right here, and then I label the velocity is in that direction. I label the force is in that direction, and then I label the magnetic field, and the magnetic field is out of the page. So I have this charged particle with a velocity. Let's see, I'm going to take my index finger and go in the direction of B. My magnetic field is out of the page, and so that tells me that my force on this particle should be to the right. But obviously it's not. So that's a negatively charged particle, yes.
So the force is always representative of the of the x-axis, or it switch sometimes?
No, it's just that when we're representing a mass spectrometer, usually we're representing it in this plane, like this. But no, the force doesn't have to be in the x direction. That if I had, well, it's hard for me to draw, but if I had a mass spectrometer with the magnetic field to the left or right, then the force would be some other direction, in the z or y direction. Okay? By the way, if I drew it over here, my force would be like that, my velocity would be like that. Right? This would be my force, and this would be my velocity. As it goes around, the force is always centripetal, is always center-seeking, and the velocity is always tangent to that circle. All right, good question. We had several other mass spectrometer questions here. Other particular questions that you want to look at on this or other exams? I'll just skim through this while y'all are thinking. Had RC circuits on this exam. This is exam 3. Home circuits. All right. Other questions?
Could we go over, number 2?
Number 2, yeah, so you will need to know all of your home devices. This device is a GFCI. GFCIs protect you from conditions, right? So like that's why you have GFCIs in your bathroom, in your kitchen, in your outdoors, mostly wet conditions where you're more prone to be electrocuted. GFCIs protect you from conditions. This is your grounding. That's that third prong. Look, we have a ground right here, that prong, but although this problem was really talking about this, the little test reset buttons. But the grounding connects your device to the ground outside of your home. This protects you from faulty devices. All right, so if you get a wire inside of your computer or whatever that's frayed and touches the case, it protects you from getting electrocuted. Oh, actually, did I read that right? No, this is not GFCI. This is GFCI. This A is your circuit breaker. Be careful, those look a lot alike. I just didn't read the subscripts there. This is your circuit breaker. It turns off if the current exceeds too much, or the allotted amount. So if you turn on too many things in your house, the circuit breaker will kick off because the current that you're pulling through that wire is going to exceed the safe capacity of that wire. And E here, E is your ground, protects you from faulty devices. D is not a thing. I mean, we do have a stable source of voltage of 110 volts in our home, but that's not our home. We just get the electricity from the provider. Okay? Yeah, this is C. The GFI turns off if the incoming current exceeds the outgoing current. Yeah, because if that's happening, then you're losing outgoing current somewhere, probably through you or your dog or whatever. I don't know. Okay?
Can we go over 13 on exam 2?
Uh-huh.
Exam 1, I'm sorry.
This one?
Is this one the one that was, I think there was one on this exam that tricked me. I don't know if it was a conceptual, oh, it might have been 12.
12. A negatively charged object has, well, a negatively charged object means that you have, this many protons, but you have more electrons. So it's negatively charged. And the way that you get negatively charged objects is by gaining negative charges. That we don't typically gain positive charges. That's not usually a thing, just because, protons are tightly bound in the nucleus, but those conduction electrons are able to move around more readily. So that's typically the way that we get a negatively charged object, is by gaining negative charges. I understand that if you lose positive charges, that also becomes negative, but that's not typically how it happens.
So
Okay.
the answer to that is only 3.
Yeah, it should have been 3, right? Is that? Number 12 is A.
Could we go
15, sure. Okay, so with a map of equal potential lines, it reads like a, what's that called? Like a topographical map. Yes, so like a topographical map. And the numbers represent the potential at that particular line. It's an equal potential line. And here I have a proton at point C. So I have a proton right here. And I want to know in which direction will it move. I always try to remember the mountain. If you remember this analogy, if I have a proton, it moves down the mountain. It moves from high to low potential. Protons do what you would expect. They move from a high potential energy to a lower potential energy. Electrons, by the way, move in the opposite direction because electrons are wonky. But the proton will go downhill. And so here I'm at somewhere between 8 and negative 12, but the potential will decrease. So I'm going from 8 down to 14. Okay, you'll see this is 8 volts, this is negative 14 volts. So it has a difference in potential of 8 minus negative 14 of 22 volts. Actually, negative 22 volts, excuse me, negative 22 volts. That's its change in potential. See, I did that. I did VF minus VI is negative 14 minus 8 is negative 22. No, that doesn't matter unless I'm asking about, point B or point A or something else. But here I was asking in what direction does it move from point C. If it were to move to point B, that would mean that the proton would be moving up in potential. It would be moving uphill, but that's not what a proton does. If it was an electron, that's what it would do. An electron would move from point C to point B, but a proton moves from point C to point D because it goes downhill. Okay? Yeah, shoot. On this exam. Yeah?
Okay, so I was confused because I thought it was EF. So it's just the electrons that move to the opposite directions.
Right, so protons don't typically move. Yeah, so here I had negative charges here, and that means that the negative charges would move over here, and the protons largely would stay the same. I get it. Sometimes we talk about how, there's a separation of charge, and we get negative ones on one side, but that's not really what happens. Really what happens is that all your protons stay where they are, and all the electrons go to the other end. So you get all the electrons down here. So the end result is that one end is positively charged and one end is negatively charged, but the protons are actually staying where they are. Sure, yeah, so I mean, if it was positive, let's erase it. Yeah, so if it were positive, if this was positively charged right here, that would mean that my positive charges would just stay where they are, but my negative charges would all go down here. Okay, so the answer would be the negative charges move to the left, protons remain where they are, which isn't an option here, but yeah, that's a good way to think about it. As you go through the test, think about, how could he change this question? And if you look back at old exams, you'll get a flavor for what that is, because that's what I do year to year. It's just the same questions every year.
It's 100 questions?
Wouldn't that be awesome? But no, it's 8 pre-response and 40 multiple choice. So it's a little bit shorter than a normal exam, but you have 2 hours. I mean, it's a little bit shorter than twice a normal exam, but you have 2 hours.
You gave us the free responses in class or something?
No, I just told you that I'll pick one free response from every exam. And each free response will have 2 questions. And I did tell y'all that at the beginning, I don't think you were here, but that the very first free response, is this exam 1? Yeah. That number 1 will be on there. But I'll just choose two questions. I'll tell you, it's either going to be C or D and E. Okay, you have to find the magnitude or the direction, which I understand that involves a whole lot of work leading up to that. And then also calculating the potential. That's why I'm telling you that now.
Can we do one on this test?
Sure. Yeah, so so if you get a question like this, you want to draw the force vectors on the question on the charge in question. So here I had a plus 2q right here. This is a plus 4q. If I draw my vectors, first, the vector due to this charge is going to be in this direction. Okay? And then the vector due to this charge. I have to be careful because remember that F is equal to KQQ over R squared. So compared to this force has a charge that's 4 times as big and a distance that's twice as big. But since the distance is squared, that means that these two are going to cancel out with one another because I have a 4 in the numerator and a 4 in the denominator. So the force due to this charge is going to be up and in this direction and the same magnitude as this force. So that means that the one that is in between, that is C, would be the right answer. But, you know, if the distance or the increase in charge is different, you could get a situation where I have a force that's here and then another force that's there that's bigger, in which case the answer would be D. Or you know, the opposite of that, in which case the answer would be B. Okay? So you have to take into consideration how the charge and how the distance is changing. Consider Coulomb's law and ask, what is this new force going to be? That actually comes up several times on the exam because we see a similar work with electric field, things you have to do regarding electric field and electric potential. If I change the distance or the charge, how does that affect the force, field, or potential?
I can't believe
I can't believe
I got that one wrong.
it either.
I don't remember. Can we do maybe?
It's a tough question, actually. It kind of is a difficult question. So you're not in bad company.
I would know, but I always freak out and I forget things.
Yeah, well, just take a big deep breath. Like y'all go on your exam, you're gonna have plenty of time. Just take a big, plenty of time, but take a big deep breath, and you know what the first question is, so you'll know how to do that really cold, and then just get started, and do your best. You know it. You do know it. You know it. Y'all do too. Okay. Don't.
Make like a B on this thing.
You can make a B. You can.
Okay, can we do 18 on exam 2?
Mm-hmm. Is this it? No, it's exam 3. 18. This one? Resistors in parallel?
Yeah.
Okay. So like for example, if I gave you this question, I could ask you for resistors in series or just sort of general rules about resistors. So even though this is just for parallel, make sure that you know all the rules. You'll know them anyway if you know the circuits well. Resistors in parallel must have the same voltage. Yeah, that's one of our basic rules, right? Resistors in series have the same current. Resistors in parallel have the same voltage. As you add resistors in parallel, the voltage in other parallel branches remain constant. Yeah, so if I have 2 of these and each of them has 10 volts, if I add another branch, then this one will also have 10 volts. So yeah, that's true. That comes up in our home too, right? As I add other branches in parallel, and every device is a separate parallel branch, then it's the same voltage. Resistors in parallel must have the same current. That's not true. That would be true if it was resistors in series. And then as you add resistors in parallel, the total current must increase. That's true. Because if I have a current here, and a current here, and a current here, if I add another branch, then it gets another current, and this total incoming current is equal to the sum of those individual currents. That's one of our basic rules for resistors in parallel as well. That for resistors in parallel, the current equals the sum of the individual currents. For resistors in series, remember that this rule, which is similar but different, this rule is true for resistors in series, that the voltage, the source voltage is equal to the sum of the individual voltages. Okay.
And for 17, like if they're going in the same direction, are you subtracting those, or not necessarily? It's just depending on where you're coming out from, maybe?
Well, remember, Kirchhoff's rules is that In is equal to I out. So anytime I have a junction, like right here, whatever currents are going in have to equal the currents going out. Now, I have a current that I don't know in this part right here, but I have 15 amps going in, but only 4 amps going out. So that means that this has to be going out, and it has to be 11 amps. Right, because I have 12 and 3 makes 15 amps going in. I have 12 plus 3 is equal to the 4 that's going out plus that current that I don't know. And so that has to be 11 amps. Then, if I look at this junction up here, I have 11 amps going in. I have 5 and 2 amps going in, so I have 11 plus 5 plus 2. That other current has to be 18 amps. So C was the right answer. I didn't even need this arrow right here. You should have known that it had to be going out in order for that junction to follow Kirchhoff's rule, it has to be 18 amps. All right? Are we going to have a multi-loop circuit? It was either free response or multiple choice, so we definitely have that. You're going to have resistors in series and parallel. You're going to have capacitors in series and parallel. This one right here, you want to do the free response? The free response? Okay. They're similar. If you know how to do one, you should know how to do the other. So here, I wanted to know the 3 currents. The big deal with these is applying the loop rule and applying the junction rule, applying Kirchhoff's rules. So I'm going to pick my loops wisely. I'll take the bottom loop. The bottom loop, because notice that bottom section does not have a resistor. And so when I write the junction or the loop rule, then it doesn't include that second unknown variable I3. My first step is just to label the directions of I1 and I2 and I3. Doesn't matter what I label, I just pick some direction. Doesn't matter, don't stress over it. And then I pick a loop. So I'm going to start here and go in this direction. So I get minus 5 I2. Because I'm going with the current, I have a negative change in potential, plus 8. Because I'm going from the low side to the high side, I'm increasing the potential of those electrons. And then I have minus 2. That's equal to 0. Notice that when I chose this side, it's really easy to solve. I get I2 is equal to negative 6 divided by negative 5. That's 6/5, or 1.2. Now, so I already have, this is 6/5. I had chosen I2 to the left, but it came out negative, so I2 is to the right. Then I can do the same for, now that I know I2, I can solve I1. I'm going to start right here and go in this direction, but it doesn't matter where I start or the direction that I go, that's just completely random. I get 3 minus 2I1. Positive 3 because I'm going from low to high potential, the little side of the battery to the big side of the battery, minus 2I1 because I'm going with the current through that resistor. I'll go down. I'm going to do the big loop here, big loop. Minus 2 is equal to 0. This one's also pretty easy to solve, so I get I1 equals negative 1 over negative 2. That's 1/2 amp. Because I chose I1 to the left, that means it must be to the right. And then finally, to get I3, I have to use the junction rule. I have I1 plus I2 plus I3 equals to 0. So when I use the junction rule, oh wait, did I, no, I chose my direction incorrectly here. Yeah, this is positive, so that means this direction should be to the left. Okay, so I have I1. Oh, and this was positive too, huh? -1. Yeah, so this was, oh, so that should be to the left too. Yes, okay, sorry about that. Y'all see the mistake that I made? Okay. So I have 1/2 plus 6/5 plus I3 equals to 0, and then I solve that for I3, whatever that is. Okay? I3 is going to be the opposite direction because it's going to come out negative. It has to be, right? Because I have all these 3 currents coming in the same junction, and I have nothing going out, so that means I3 has to be wrong in direction. Okay? Know how to do multi-loop circuits. It'll come up, 2 or 3 times on the exam. What else?
How do you know whenever you have a dark spot versus a bright spot?
Okay, good question. Yeah, so if I look at my interference pattern, whether it's double slit or diffraction. Double slit and diffraction are exactly the same. By the way, since single slit was not on your exam, it will not be on your final. So even though it's in past exams, it's not going to be on your final. This is my 0th order. That means that the path length difference, I'll call that delta L, is equal to 0 wavelengths. That there is no difference. So when I'll have 2 light rays coming from 2 separate directions. The difference in their 2 path lengths, the distance that they travel, is 0. They're traveling the same direction, the same distance to get to that point. But right here, this is my 1st order. That means that the difference in their path lengths is equal to 1 wavelength. That means that I have 1 ray that's traveling from here, another ray that's traveling from here. Notice that 1 travels a little bit farther. It travels farther by 1 wavelength. And then likewise here, this would be 2 wavelengths and on and on. 3 wavelengths is my path length difference for my order numbers. So if I have a path length difference, delta L, that's equal to some integer times the wavelength, or actually we used M, right? That's our order number. Then this gives me a bright spot. We have that in a question. I'll go to that and show you in just a second, where we actually had to say, I gave you the path length difference. Like I said, 1 wave travels 3 meters, 1 wave travels 4 meters, or we'll say 5 meters, I think was the answer. That's a path length difference of 2 meters, and I told you that the wavelength was 2 meters. Well, this is equal to 1 wavelength, so I had a bright spot. I think those actually were the numbers that we had in that problem. Okay. On the other hand, if I'm going to a dark spot, this has a path length difference of 1/2 wavelength, 3/2 wavelength, 5/2 wavelength. This is 1 wavelength, 2 wavelengths, and on and on. So you see I have 0, 1/2, 1, 1.5, 2, 2.5, and on and on. Okay? That came up 2 or 3 times on the exam. So it is an important idea, an idea that you'll probably see on the final. Does that answer your question? Yeah.
Draw out the diffraction formula and label with each.
Sure. Yeah. So if I have, let's do double slit because it's a little easier, but the same will work for our diffraction grading. I'll explain to you what that means here in just a second. So remember, the squiggly line just represents the intensity of the light. So here I have my brightest light right here, and then I have a little dimmer light and a little dimmer light, dimmer, dimmer. So that's why the squiggly line looks like that. It's an intensity graph, a graph of the intensity of the light. This distance is the slit separation. That's D. This distance is the distance to the screen. That's how I describe it in the words. And that is the distance L, we call it on the equation sheet. This is the order number. This is M = 1, m equal 2, etc., on and on, m equal 3, m equal 4, it goes up. This is also m equal 1, m equal 2. That's our order number. And then if I want to know the distance to a particular order, say I want to know the distance to m equal 2, that's y. This angle, if I'm going to the second order, this angle is theta. So that all comes into the equations, d sine theta equals m lambda, and then y equals L tan theta. That's just an application of our trig, our SOHCAHTOA. So this is our equation for double slit and for diffraction grating. The one difference for the diffraction gratings is that the diffraction grating, instead of having 2 slits, has thousands, millions even, of slits. And so if I want to know the distance between those, I would give you, say, 10,000 lines per centimeter. A line is a slit, but we just usually call them lines. Sometimes we'll call them slits. But a line per centimeter. If I want to know d, I do 1 over 10,000. Be careful because that's going to be in centimeters, so you'll need to move that decimal place 2 places over. So that's how diffraction gratings are different. That was in your free response, I think, for that exam, where you had to do that and calculate y for a diffraction grating. Cool? Yeah.
For number 14 on exam 4, it's basically like conceptual. They ask you, you know, what happens if you manipulate this variable.
Yeah.
Can we go over that?
Sure. So I'm just going to write those equations. D sine theta equals m lambda, and then y equals L tan theta. If I talk about the width of the central bright spot, the width, where is it? Okay, here it is. If it gets wider or narrower, I'm really asking you what happens to y. If it gets wider, that means that y gets bigger. If it gets narrower, that means that y gets smaller, right? Because y is the distance to those different orders. So I really want to know, I'm asking what happens to, not the central bright spot, but what happens to y? If I move the screen farther from the grating, well, this one's easy, because I'm increasing L, that's going up. Theta remains constant because I'm not changing anything about the diffraction grating or the wavelength or any of that. So if L gets big, that means that y gets big. So the central bright spot gets wider. If I imagine my double slit, or this is a diffraction grating, but you know, they're the same. I have these, wait, is this going to work? If I have a screen right here, then I have my bright spot there, and my dimmer spots here. You can imagine that they have these lines going through them. So if I move my screen back now, then my spots are now going to be here, here, and here. Yeah, the angle stays the same, but you're moving L out, so they spread out because they're diverging. Is that clear? Okay. And that comes up, I think it came up a couple of times on your exam. Yeah, it came up again here. Okay. Yeah. Well, I don't know if we went over any. Yeah, I mean, you know, we did the forces. Let's just sort of skim through it. If y'all have ideas or things you want me to point out. Sure. So if I give you an electric field map, what you do is you look, I'll have to have given you one of the charges. So here Q1 is 3 coulombs. Q1 is 3 coulombs. And notice that the field lines are going out. That means it has to be plus 3 coulombs. And then I want to know the sign and magnitude of Q3. Notice that the field lines are going out, so it has to be positive. So I can get rid of those. Also notice that it has more lines than Q1. So that means it can't be that or that. It has to have a bigger charge. So I don't really have to go any farther than that. A way that I like to do this is to assign a charge value to each line. So since I have 3 coulombs and I have 3 lines, that means I have 1 coulomb per line. So if I have that, then that means I have, let's see, I have 1, 2, 3, 4, 5 lines right there. That means I have 5 coulombs. Or I have 1, 2, 3, 4, 5, 6 lines right there. That means I have -6 coulombs. -6 because the field lines are going into there. Yeah, so it has a negative charge. Okay? That's a great way to do it. It's especially helpful if you don't have an integer number of coulombs per line, because then it becomes, like if this was, say, 0.75 coulombs per line, then it makes it easier to do that calculation. I try to keep it at an integer value, but it doesn't always work. Okay? Other questions? Exam 2 was, is this exam 2? Yeah, resistors and capacitors, circuits, which, as I said, every exam is equally represented. So, and I try to equally represent the different sections of each exam equally, so that you have a good distribution of questions. Yeah, mostly I'm just going to be changing the circuits on this exam, giving different circuits but similar questions. Okay. Now let me know if you want to do anything here.
So when the distance between the slits are doubled, it goes to 1/2, and then when the distance between the screen and the background doubled, it multiplied also.
Yeah, so if the slits are moved farther apart, let's do that, d sine theta equals m lambda. If I double the distance between the slits, as I double this, that means that theta has to halve, all right, in order. In these things, we're taking this assumption. We're taking that theta is equal to sine theta is equal to tan theta. We don't really talk about this in class, but that is an assumption that we're making because they're usually small angles. Not always, but they're usually small angles, so that's true for small angles. But that's beside the point. So if that happens, then I say y equals L tan theta. So if sine theta is halved, that means that tan theta is halved. And if tan theta is halved, that means that y is halved. So if I increase d, if d goes up, that means that y goes down by the same amount. I don't know if that's what you said. Is that what you said? Yeah. I always forget. I have to write it down and go through all the variables and think about it. It's actually opposite what you would think. That you would think that if I make my slits go farther apart, then the pattern would go farther apart too, but that's not true. That's not what happens.
What I try to imagine, like the screen where it says number 14, it says like you move the screen back a little bit.
Mm-hmm.
You move light further away, makes it look like a bigger spot. Like that. Is that?
Yeah, if you move the screen farther away, yeah, absolutely, yeah. Yeah, that's a good analogy. That as I move farther apart, that spot gets bigger. Because you have an angle, so you have angles that are constant, but as I move back, they get farther apart. Yeah, they're divergent. Okay? Is that okay? I'm going to stop this in this room.